is that, can you see, all of you, this screen? And this is the same question for the other screen as well. Who doesn't like this screen? I want to know that, do you see everybody this screen as well? Because I'm walking around a lot. I just make sure that you can see both the screen. Okay, a non-equilibrium calorimetry. As Edgar told and Faezeh, I'm working with Professor Christian Maas and in KU Leuven University. This castle is in our campus. And whatever I learned from this topic, non-equilibrium calorimetry, is from this group. Okay, and the content. First of all, I give you historical introduction related to equilibrium and non-equilibrium system. And then we will see what is non-equilibrium calorimetry, and then how we can calculate it, define it, and how even we can measure it in experimental setup. And the last thing is that what are the features, what are the property and information that, okay, you define it, and now which property it can give to. First of all, before this slide, can you tell me about equilibrium system? What do you know about equilibrium system? If you want to introduce equilibrium system, which property you assign for that? Do you know that? Just tell something.
Time reversibility.
Oh, good. It's a bit advanced. Good, time reversibility. From entropy production? It's okay. It's too advanced. And from your side, what is equilibrium? Just if somebody from the street asks you what is equilibrium system, what are you telling me? Don't tell about the entropy production. What do you tell about the equilibrium? Are you, your body is in equilibrium or non-equilibrium?
When you have two bodies, they have the same temperature.
Wait. You?
When you have two bodies in thermal contact,
Uh-huh.
they have the same temperature.
Okay, good. Thermal equilibrium. You?
The net force affecting the system equals 0.
Okay, there is no external force. It's your meaning? There is no current. Your system is isolated. Okay, here the property is passive. There is no external force, for example. It's time reversal, and it's one property. But it's we are working in non-equilibrium system, then we claim that, oh, equilibrium is very boring. But it's not like that. Actually, it has some interesting point as well. The fun part is people really like to look at the phase transition. Okay, even in equilibrium, you can understand a lot about the system. And okay, but in general, it's rather, it's more similar in the sense of universal property you can assign to your equilibrium system. Just imagine, what is my meaning of universal property? For example, just imagine the air in equilibrium, of course not when window is open, and or the piece of iron, water. All of them you can describe them with Gibbs formalism. Do you remember the Gibbs formalism? With the story of partition function and macros, the canonical ensemble, grand canonical. This story that we have it in, a statistical first course. Okay? And this is a universal property that just with Gibbs formalism you can define them. It's nice but boring. Okay, for example, we are interested to see the probability of certain magnetization for a given state, how many, who likes the entropy, how many ways you have to reach in this state, and then the meaning of entropy appear here. Okay, and entropy. In equilibrium, you see, I mean, if you want to just gather all of the information that just basic formula that you do have in equilibrium, you see, everywhere is S. S is appear everywhere. I'm a bit exaggerating. You can find something that S is not there. But okay, I like to, you assume that you need entropy a lot, okay? There are some formulas just for review. By the way, if you just search them, there are good information. You can learn about that. This formula just for review. But now entropy is really important. Can you tell me now, entropy is really important in equilibrium, how you measure the entropy, how you calculate the entropy? Any idea? For a given system, I give you something and then I'm asking, oh, what is the entropy of this system? Oh, okay, good. You shouldn't answer immediately, you know. I want to play. No, but it's good. But in the first formula, what you need, what is the main ingredient?
Heat.
Exactly, heat. We need heat. Okay, this formula is really important. Of course, I'm in equilibrium and I'm speaking about the reversible heat. Okay? And this heat is coming, of course, from the first law as well. We will describe this, I will explain more detail. But another way how you measure the heat. What is the quantity to speak about the heat? Here, heat capacity appears, okay? And this thing is called calorimetry. You measure the heat in the system and heat capacity in the system, and then it's called calorimetry, equilibrium calorimetry, okay? And now, just somebody tell me what is the definition of the heat capacity? The level of a school, don't tell me, very advanced definition, okay? I myself cannot manage that. It's just somebody tell that, what is the definition of heat capacity? Just first idea that you have. You?
The amount of heat required to raise 1 degree of temperature.
Yes. And if heat capacity of a system is too much, what does it mean? It's high heat capacity. What does it mean? For example, water and sand. Water heat capacity is 4,000.
It is store heat and it is good place to store heat.
It needs too much heat up to change the temperature, no? It needs, but sand, for example, you can immediately heat, the temperature you can immediately rise. With water, you should give the heat to that. Okay, this is the basic, you see, we are in a very basic and fundamental definition, but really it's important. This is a basic definition of the heat capacity. Oh, sorry, why it's like that? Okay. I don't know why it's like that, but this is a basic definition of the heat capacity. You change the temperature, and then heat, you look at the heat, and the heat capacity appears here. Okay? And this is the main formula that we have for the entropy. The heat capacity is here. Okay, but why? Heat capacity not only can give you information related to entropy, but it's not trivial. You see, we get used to with it. We say that, okay, heat capacity, we heard a lot. But just think deeply. Each material has its own heat capacity. It can identify the material. It's the characteristic property of a material. So it's not trivial. It's universal for each material, of course, in a fixed temperature. Okay, for example, the numbers that I gave you here is for the room temperature, with temperature changing. Okay, so the property is that it's constant. It's really important. And the other things is that it can give you information related to entropy. Each of the word that is here, you can search it. It has one formula behind of that. It can give you information related density of a state. You can understand about the energy gap, for example, in a discrete space, and the degrees of freedom. Okay? Or for example, for the heat capacity of gas, it's not, we used to with it, but it's not trivial. Look, it depends on the degree of freedom that gas has, a translation, a rotational or vibrational degree of freedom, that it depends on the structure of the molecule that you have, a 2 atom, 1 atom, or this kind of thing. And then you have heat capacity, constant heat capacity for gas that you have. So it's important. That's why Maxwell thought that I have now put before you what I consider to be the greatest difficulty yet encountered by the molecular theory. It's related to kinetic theory. About the metal, look, heat capacity of a metal in high temperature is going to be a constant number. It's universal. But about the low temperature, it was a time that it was a big question for them. They couldn't realize what's going on in low temperature for the heat capacity. Why it's behaving not as 3R. Why it's behaving as range. It's going to 0. This is a question. Why it's going to 0 and how it's going to 0, in the sense of which speed and what is the function to going to 0. Okay? And this is, by the way, this is the law of the long petite for the high temperature. And for a lower temperature, NERMS had one experiment that measured the heat capacity and saw that whenever it's going to 0 temperature, the heat capacity also is going to 0. Delta S is going to 0 at low temperature, S entropy. Do you know which law is this law? When heat capacity is going to 0 at 0 temperature? Debye is telling that how the heat capacity is going to 0. The T to the power 3. This is Debye. Yes, excellent. But what is this law that heat capacity at low temperature going to 0? What? It's third law of thermodynamics, no? Third law of thermodynamics. The Planck version is telling that entropy is going to 0. Nernst version is telling that heat capacity is going to 0 at 0 temperature. Okay, this is important law of thermodynamics that we do have. In some moment, Einstein and Planck, with the quantization of the what is this one? New frequency, they could understand why heat capacity is going to 0 at 0 temperature, and Debye with not with quantization, actually exactly with continuous distribution that gives for the frequency, could see that, heat capacity can calculate the heat capacity, and then see that if you take a limit of the t going to 0, it's behaving t to the 3. Okay? Each of them, they have a very simple and nice formula. You can just search it. I hope you can find it in Wikipedia as well. Or nowadays, ChatGPT. Okay. Now I give you a simplest example that exists in equilibrium. Just two-level system. Two-level system, I have two-level system with the energy gap between epsilon. Okay? I have a particle jumping between these two levels. And I want to measure the heat capacity, not measure, I want to calculate the heat capacity of such a system. The only information that I have is that, the energy gap is epsilon. Do you know that how we should calculate the heat capacity? I think here is a minus error. It should have a minus error, I think. And do you know what is this average? It's just simply this one, I mean. It's over a state. I mean, here is 0, and it's 1 and 2, and the stationary of each state with the energy that they have. Here, if you can imagine, the energy around the state is 0, the other one is just epsilon. Okay, and then take a derivative. And what is the rho? Just Boltzmann distribution. I mean, just e to the minus beta to epsilon, I mean, to energy that it has. And then you calculate the heat capacity. Very simple. But look, what do you see here? Instead of heat capacity just going to a constant, it has a strange peak here. Look. This peak is called a Schottky anomaly. And can you understand, can you feel, what is your guess why this peak appears in the heat capacity? What's going on here? I don't want you to tell me exactly the reason, but what's going on here? What do you feel? Your guess, your feeling. If you tell very professional, then I'm doing nothing here. Just give me your feeling. What is your feeling? What's happening here?
What I can feel is like at higher temperature, the population upper levels are too much crowded, but then to relate it with decreasing, it's somewhat becoming hard for me to understand.
Yes.
I mean, like, of course, it will take me more energy to put another particle on top.
Yes. Yes, correct. I mean, could you hear me? It's related to population. Remember this word, because I will back to this property. It's related to population. At the first, everything is in ground state. You give heat to the system. When your heat is comparable with the gap, you see, the gap is epsilon. When your heat is comparable with the gap, then the particle will start to go to higher, the other level, the higher level. Okay? And then distribution between two levels, just almost the same. So the rest of the heat is just increasing the temperature. I mean, something happening here at the first, you are pushing the system to go to higher population, to higher level, changing the population. And then the rest, it gets a bit similar. Of course, this interpretation is very naive. But if you want to just know that from where this peak is coming, it's from the gap. Okay? And this is for two-level system in equilibrium, and we can calculate the heat capacity of such a system. Now, what about a steady non-equilibrium system? Okay? So far, we were in a boring world, universe, passive, everything. Of course, it has own beauties, but we are alive, no? I hope we are alive. And then we want to understand what's going on for a non-equilibrium system. Can we define non-equilibrium heat capacity? The heat capacity in non-equilibrium system. Can we define heat capacity in non-equilibrium system? If yes, which information can give you? What you can understand about the system. For example, in equilibrium, you could understand about the gap. We already discussed about that. You could understand about the entropy, the characteristic property of a system, because it was constant. Which information can give you in non-equilibrium? Okay? What is the approach here? We are interested to thermal response. What does it mean? I put my system, my non-equilibrium system, in a big bath. The bath is in equilibrium. Temperature is well defined on that. Okay? The bath is in a fixed temperature T. And the system itself is non-equilibrium. Why? Because the current's over that. The work is done on. It's not isolated completely. Okay? And now I'm perturbing the temperature of the system slowly, I'm emphasizing on that, and a little bit. Okay, but you can go far from, the temperature, you can do it up to changing a lot. Okay? And now we are looking at what is the excess heat of such a system. The system first is at a steady state, means that it's exchanging heat with the environment. When you perturb it, then it started to again exchange heat with the environment and relax to another steady state. We are interested in this excess heat. Okay, this is the heat capacity that is defined in 2019 by Christian and his colleague Karel Nitokny from Prague. That is defining, instead of a Q reversible, you do have excess heat. Okay, and by the way, this one is just the setup of experimental for the AC calorimetry, how people measure the heat capacity, but we will back on that. Now I have a system that it's in non-equilibrium, but again, the simplest system that I do have. It's a two-level system, same as two-level system that we had in equilibrium. And the particle is jumping between these two levels, but there is another dynamic for your energy landscape. There is one dynamic for the particle itself, and there is now another dynamic I'm adding to the system for the energy landscape. And I have two possible landscape of the energy, plus and minus. There is one dynamic that with the rate alpha, the landscape plus is changing to minus and vice versa. And the energy gap here, I don't know why, but it should be epsilon. I put it mu. Sorry for that, but energy gap is mu. And I have another things here is the barrier. This delta. Okay? This delta in equilibrium also, it was there. But in equilibrium, it's not playing role. Because if you just calculate this rho, this is symmetric part, it's just cancel. Numerator with denominator is just cancel out. But in non-equilibrium, this barrier play role. This barrier is symmetric part. Why I'm calling symmetric part? Look, the particle, it's either here or there. See the barrier the same. Okay? And now what is the dynamic? The particle, if it's in a plus, this green landscape, okay, it's there, for example, in a state 1, and the plus is changing to the minus, nothing happening for the particle. And the particle is now jumping from a state 1 to a state 2. Now it's exchanging heat with the environment. And then here again it's in yellow, and then changing the landscape, switching with the rate alpha, nothing happened. But if jump from a state 2 to a state 1, heat is exchanged with the environment. So whenever I'm changing the level of the energy, the heat appears. Okay, it's important. In your system, in any given system, it's important how you realize the heat. And you can find the heat in your system. Okay? And now you don't know anything about how, yes?
Sorry. Question on the model. So, where does temperature enter here? Because I guess the jumps in each of the potentials are triggered by thermal calculations, right? But this depends on T. The higher is T, the more jumps you have up here.
Yes.
But does temperature influence also alpha?
No, here not. The transition, it depends how you defining, of course, your dynamic. But the dynamic that I'm defining is that I have a state 1 to 2. I have transition rate for them. And the transition rate is temperature here, epsilon 2. And for the, for example, plus, it's like that. For the plus, yes. And for the minus, it's just convert. I'm just giving one of the 4 rates here from the 1 to 2. The temperature is here, but for the alpha, no. I want to tell that the heat that you want to look at it, that it's not dependent of the alpha rate, but the alpha rate makes your system non-equilibrium. Yeah, but the heat is here with the local theta valence condition, of course. Yes.
Since it's a two-stage system, temperature would be negative.
Negative?
It would be negative in a two-level system. The shape of the entropy on equilibrium noted that when we derivated in respect to time,
Mm-hmm.
sometimes the slope is negative.
Okay, I can understand your meaning, but can you just imagine that the temperature here is positive? For this rate, if you want to consider negative, I will change my rate. But I don't know, it was a question?
It can happen here, or
I didn't consider it. We are not considering. But for me, very naively, if you want to change the temperature to negative, it's just for the matter of a scale for me. But we do have something, I will back to effective temperature, later in my talk. Maybe there we can speak about that. But here, just forget this kind of thing. It's okay? Okay, now I didn't tell you how you want to calculate the heat capacity. This is another story. Just imagine in such a system, I'm looking at the excess heat and perturbing the temperature beta, for example, and everything. Now I plot the heat capacity, but from where it's coming, just accept from me. Okay, I want to just pay attention that we can plot the non-equilibrium heat capacity here. Just first the properties, and then I will back for the calculation I'm measuring. If delta is 0, the heat capacity, look how nicely behaved. Such very similar to the equilibrium. It has a nice peak, and it's comparable with the gap as well. But if I change delta, look how behaves the heat capacity. Heat capacity can be negative. Have you ever heard or seen a negative heat capacity?
Really, a case in water, like in 1000 degrees, it has a heat capacity negative. That it means like the heat change the direction. I don't know, but
You are giving heat to the system, but get cooler.
yeah.
In a
It's like when you have a liquid water less than 0 degrees, but equal with a heat or something like that, it gets frozen. It's something like that
Oh, you mean that in the phase transition you want to tell, in the latent, related to latent heat? Yes, people, I saw that they are defining for the negative heat capacity and latent heat as well. I mean, the heat that you are giving to the system, nothing is happening. It's just phase transition. Okay, is it giving to the system heat? But it's just changing the phase. The temperature is not changing. You are giving?
No, but it's I don't remember the Faezeh, no, not the Leuven.
Oh, okay, sorry, I
But
misunderstood.
I saw something because students asked me
Okay.
that if it is possible, and I see that it is the
I
only
see.
things.
Okay, sorry, I don't know about that. But whenever,
Which material?
Water. Water.
Water.
yeah, but you know, I mean, the high energy physics people, whenever you ask them this question, they say, yes, black hole. And yeah, it's true. It's true. They saw, I mean, it's true. The black hole heat capacity is negative, but they are telling that, oh, Faezeh, look, this is equilibrium and you have negative heat capacity. And we non-equilibrium people will tell them, no, this is non-equilibrium that you saw with negative heat capacity. But okay, there are some discussion there. Have you ever heard about that? They know something about it, and it's interesting. Look, if I change just the barrier, the symmetric part, heat capacity can be negative. Forget the negative. Heat capacity is changing. Why this symmetric part is effective on the heat capacity? And we're surprised for negativity, but it's changing the behavior of the heat capacity. Okay, so I can tell that, look, in non-equilibrium, heat capacity can give you information related to kinetic part that you don't have it in equilibrium. It related to symmetric part, okay? And this is very important and nice. And just to summarize it in two-level system, look at two plots I have it. And if you change the delta, it can, some strange things you can see. And another thing is, I just pay attention to other peak here. The peak that was important there, and you can see it, and then vice versa here. And the question is that, oh, it's going to zero. Inertia theorem. Is always going to zero? Yes.
So it's delta. In some way, it's measuring the asymmetry of the delta.
Yes.
And then, there are these ratchet models for commercial models where these are symmetry. Obviously, I'm not saying because I don't have much, but it's a sense of the generate motion in active systems. Rather than symmetry, is classic potential.
Uh-huh.
Sorry, I'll tell you a delta is even means there are two wells with the same height.
Okay, that I don't know there, but I can say that here we are telling as a symmetric because, okay, the two level that we have, they have gap distance between them, energy different, it's different energy distance they have. They are not completely in the same level of the energy. And now forget either they are in the same level or not. Both of them see the barrier.
Okay, understood. That is the barrier.
Yeah, it's the barrier.
Height of the barrier.
Yeah, it's the height of the barrier. Did I answer your question?
Yes, yes.
I don't know. I just explained something. Okay. I don't know. But by the way, it's here. The symmetric part is here.
Thanks.
Yeah. Okay. And okay, so the heat capacity, just in this example, you have, yes.
I had a question regarding the previous slide.
Yes.
Your alpha is like flipping rate of this.
Yes.
potential.
Yes.
And so if your alpha value is small, so you are flipping it at a larger time scale, right? So,
Mm-hmm.
if you flip more fastly, then it should be more non-equilibrium like, but your peaks, when your flipping is faster, it's decreasing sort of.
Yeah, it's a good question.
I thought non-equilibriumness was creating this.
No, it's a good question. The point that is happening when you are, it has threshold in the sense that when you are increasing alpha, then the switching between two landscapes get a lot, okay? And then it's going to be similar, the population in each level. So, yes. It's something, it has a threshold here. I cannot tell that it's completely equilibrium, but just consider the population that here also is happening. In the sense that they divided in now in the same, they are accessible together. They just go and back and then doesn't matter. They no longer see the landscape. They're just divided similarly. It's just like that, okay?
In the plots, second plot, what happens if we made alpha like the first one, like 0, 1, 2, 4? We don't have a plot.
Mm-hmm.
I see that when it is 0.4, the red line is like very close to 0. So if it is bigger than 1, in the second plot, when delta equal 2, when alpha is bigger than 1, we will not have a change in the heat capacity?
No, it's a good question. First of all, in this system, if you suddenly put alpha is zero, you are destroying the system because we couple them first of all.
No,
Yeah.
I mean why is the two graphs don't have the same alphas to compare? So we want to compare them like when delta is 0.
Yeah, sorry, because the scale was too much. If you want to just compare it, whenever is delta 0, you see here you do have non-equilibrium term, but delta is 0, behavior is not changing. Okay? If I'm in equilibrium, I mean alpha 0, you change the delta, the system doesn't feel it.
Not 0, 1 or 2, because here alpha is smaller than 1. So
Yes.
if alpha is
If
bigger
you just increase the alpha too much, it's the same question. If you increase the alpha too much, you expect, oh, yeah, I'm going to the non-equilibrium, then I should destroy the system far from equilibrium. But in this system, it's not behaving like that because they get accessible together. And then if alpha is too much, it's kind of going to equilibrium again.
so basically we'll have
You have threshold. Yes.
Because I kind of see it in alpha equal
Yes.
0.4. So basically, as you get close to 1, you are going into equilibrium.
Yes.
You will have nothing.
And it's
Nothing
very
interesting
dangerous.
to look at.
Yeah, it's very dangerous if I tell that you are going to equilibrium because it's not quite equilibrium. Even if you I give you the expression and you just take a limit alpha go to infinity, it's not the same as equilibrium calculation. It's not the same, okay? But you are killing your non-equilibrium term in it, okay? But I can give you intuition, I mean, just why it's happening. Because the two-level system, if I can model it, because I work on the graph and discrete space, if I model it, this system on the graph, it's 0, I mean, it's state 0, 1, 1, 2, it's plus and minus. I have 4 states, and alpha is here, the energy gap is here, and just imagine I increase the alpha, what's happening? Whatever is there is accessible to this one as well. Whatever is there is accessible to this one.
So the states merge.
Exactly. And they are fixed, I mean, they are just coming together, and it's same as two-level system. Just two-level system in equilibrium. Okay? Okay, what was I wanted to tell? Pay attention about the zero temperature behavior of the heat capacity. Pay attention that it can possible you have negative heat capacity. And another property, we change the delta, something happened. Means that now in non-equilibrium, kinetic information plays role. It's important. Okay? I don't know. Can I keep continue or is a break?
What do you think? Go on. Break?
Break.
There is a call for break.
It's okay.
But the time was
I don't know about the time. I just, do we have time? Look, I think 5 minutes I have, no?
yeah, there was officially a half an hour break. To, you want to continue? You want a break?
I think, we should not necessarily follow all this written word. We can also self-organize, okay, depending on
Who wants to do a break?
Okay.
so maybe how much will it take to get to a point where a break would be?
I can manage it in any time. I don't know, maybe, maybe in 5 minutes we can go to break. It's okay? Can you survive for 5 minutes? Can you accept me for 5 minutes? Okay, and now just 5 minutes. Sorry, I promise you 5 minutes and I'm not keep speaking. Their main question remains that Okay, Faezeh, you speak about the non-equilibrium heat capacity, but how you can measure it, how you can calculate it, what are the methods? In theory, the good method is quasi-potential and experimental setup and maybe working with diffusion process. The good method is AC calorimetry. And recently we started to collaborate with experimental people for AC calorimetry. It's very interesting. And now you calculate it, you measure it, what are the features, what is the heat capacity in close to equilibrium, when and how you have negativity, and what about the inertia theorem, my PhD thesis. Okay? And now, if you want to define it, it should have meaning, no? I mean, something that is very well motivated for deriving active particles that you can measure that. I first start with quasi-potential, and that is solution of Poisson equation. I'm not giving you too much technical stuff, but just definition. Do you remember I told you I have a bath? I'm perturbing the temperature of the bath. Then we are looking at excess heat. I told you be careful, slowly we are perturbing that. And it was something that I emphasized on that. And now this is just a cartoon. That your system is in a steady state, it's exchanging heat with the environment. This P is heat power, okay? And then you change the temperature of the bath, the system disturbs, and you perturb it, and now it's relaxing to another steady state. We are interested to this area, the integral of this area. And of course, it depends of, it depends, of course, to excess heat as well. And then we are looking at this animal, this quantity, we call it a quasi-potential. This is the definition of quasi-potential. I hope you get familiar with this kind of notation, but if not, don't worry about that. It's just taking the average over all of the possible trajectory, that if you start from the x, and we take the average of all of the possible trajectory, and we are interested to the long time behavior. Okay? But everything is happening in quasi-static limit. This thing that I was emphasizing on that, be careful, slowly is in a quasi-static limit. But if you want to just touch that, what is it? It's just in equilibrium. If I just take a limit for the equilibrium, it's just the energy. It's nothing strange. And then here, this is a generator. And if I apply on this heat power, I mean, this one is equal to this one. It's a time evolution of the heat power. And if you just take the integral, it gives you this. This is just solution of this. I mean, just take the integral, exponential. Then you have Poisson equation, generator with the source. For any given source heat that you do have, you should solve it and find what is V. And okay, this V, yes. Yes. Can I write something? Yeah. I mean, here. Yes. Heat capacity, we define it as follows. The excess heat. And now, what is heat? I'm looking at first law. Just remember these things that is coming. But okay, here is not that much related. Now Qx is just here. Is that the integral is it? And now in the quasi-static limit, what it has a proof. In parameter space, for the excess heat, our parameter space is, we are changing only temperature, but it can be everything. In quasi-static limit, in parameter space, if I look at the excess heat, disappear. But you see, what is excess? Because I'm looking at the average, I mean, the excess of something. For example, quantity, I'm just defining spontaneously. It's rho x. When epsilon is too small, and I mean, here you can understand what is excess heat. You see, why I'm telling excess? Because I'm looking at two steady state. And from here, I apply quasi-static limit, disappear, and this V is exactly the C. And it's related to the heat capacity. Is it okay? Yeah. And we are solving this Poisson equation, and then heat capacity as this one. I mean, the main ingredient is that what is quasi-potential. And to find quasi-potential, you need to find to solve the Poisson equation. If you are in a discrete space, your generator is just Markov-Chain process, for example. I mean, this is the Kirchhoff matrix with the transition rate matrix. If you are in diffusion limit, diffusion process, L is different. But Poisson equation is still there. Doesn't matter which process you are working on. You should solve the Poisson equation, find the quasi-potential, and then apply it here. Then you have heat capacity. Do I have time? Yes, it's okay.